Hello, good morning. Myself, Dr. Lakshmi Devi, Professor, Department of ECE, St. Peter's Engineering College. Today I am going to cover a basic subject of electronics, like electronic devices and circuits. Under this topic, introduction of passive components. Already in the last videos, I have completed introduction of electronic devices and circuits, and in this, passive components and how we are going to have connection with the passive components and what's meant by the node and in what way have KVL and KCL applications. As an introduction first, before starting these concepts of electronic devices and circuits, as a second year first semester students, it's very essential to go through these concepts. If you have understand the concepts of passive components, then you are in a position to understand the circuit diagrams as well as applications of Kirchhoff voltage law and Kirchhoff current laws. Let us see here first what are the passive components or passive elements we are having. There are three elements: resistors, capacitors, inductors. And this resistor, the property of a resistor, capacitors, and inductors might be completed these concepts in the inter second year itself, but still, which opposes the flow of current will define it as an actually the resistor. It's an actually the symbol of resistor. We are showing three peaks at the top and three peaks at the bottom. This is an exact way of representing the symbol of a resistor. R, denoted with the letter R. The current flowing through the resistor we are indicating like I, and drop across the resistor is a voltage V. Either drop or voltage or potential. These are synonyms of a voltage. Then capacitor, which stores energy in terms of electrostatic field, that we are representing with the capacitor C, denoted with the letter C, and this is actually the symbol of capacitor, and current flowing through the capacitor is denoted I, and drop across the capacitor is also a V. So similarly, inductor is another passive element, and this energy is stored in electromagnetic form, and the current flowing through the inductor we are representing as I and denoted with the letter L, and the drop across the inductor is also denoted with the letter voltage V. These are the notations or the symbols of passive components like resistor, capacitor, inductor. V is equals to IR. By applying Ohm's law, just we have the drop across the resistor is V is equals to IR, and current flowing through the capacitor I is equals to C dV by dt, and voltage drop across the inductor V is equals to L di by dt. In this, we are observing different notations of the formulas. Current flowing through the capacitor, we are writing I is equals to C dV by dt. And if you want to know the drop across the capacitor, just you have to integrate on both the sides. Then we are having V is equals to integral of I, that is V is equals to 1 by C integral of I dt. That's a formula for voltage across the capacitor. Similarly, here V is equals to L di by dt is there. Suppose if you want to know the formula for current flowing through the inductor, you have to integrate this particular formula once, that is I is equals to, if you have integrated, then you have I is equals to 1 by L integral of V dt. These are the equations of voltage and currents for the inductor, and I is equals to C dV by dt is the current flowing through the capacitor. V is equals to 1 by C integral of I dt is current voltage drop across the capacitor. V is equals to IR is the drop across the resistor. Similarly, I is equals to V by R is current flowing through the resistor. These are the basic formulas for measuring of current as well as voltage through this particular passive elements with the basic formulas. Let us see now what type of different connections we are having in the circuits. Means these are the basic connections, series or parallel connections. So if two resistors are connected in series, in what way we can calculate the equivalent resistance? If I mean, resistors are connected in parallel in what way? Just you can observe here. Resistors R1, R2 are connected in series. So equivalent resistance R is equals to R1 plus R2. And in case of parallel, R is equals to, that is, R is equals to, in general, we have 1 by R is equals to 1 by R1 plus 1 by R2 plus 1 by R3. Or otherwise, we are representing three resistors are in parallel here. If similarly like this, if two resistors are in parallel, R1 R2 by R1 plus R2. Or otherwise, whatever may be the number of resistors connected in parallel, R is equals to 1 by R1 plus 1 by R2 plus 1 by R3. Like this, if you go for the equivalent resistance calculation, in case of parallel, we are going to have the equivalent resistance for the parallel combination of resistors. Similarly, inductors. Inductors is the same as resistors, like calculation of equivalent inductance in case of series, equivalent inductance in case of parallel. Same L1, L2, L1, L2, L3 are connected in parallel. Same formulas in case of resistor as well as inductor. But while coming to the capacitors, the formulas are opposite in this. Uh, Capacitors are connected in series means C1, C2, C3 are connected in series. C is equals to 1 by 1 over of C1 plus 1 over of C2 plus 1 over of C3. And similarly, if the capacitors are connected in parallel, C is equals to C1 plus C2 plus C3. It's in case of capacitors, it's opposite with the calculation of resistors as well as inductors. So these are the formulas if the components are connected in series as well as in parallel, three different components of electronics, that is passive components. Coming to the next, connections and sources, in what way we are having in the circuits. The ground connection we are representing with this particular symbol, that's a reference for 0 volts. Node connection, whenever the two or three points join together, or more than that, three points also join together at a single point, that particular point we'll call it as an actually the node. That is voltage level the same everywhere on the node. For this, from this particular point to the ground, reference ground, it appears to be the same voltage. That particular point we'll call it as a node. Then voltage source, there are two different types of voltage sources, two different types of current sources: independent, dependent. Independent voltage source we are representing with this particular symbol of a circle consists of plus and minus. It's an independent voltage source. Dependent voltage source having this diamond shape inside plus and minus. Similarly, current source also having the same notations of independent current source and dependent current source. Independent current source having circle with the arrow indication towards the direction of current flow, and dependent also in the diamond shape having the same current direction. These are the connections and sources symbols. Coming to the circuit connections here, these are different examples here we are observing R1, R2, R3, R4, R5, R6. Totally 6 resistors are connected. V1, one voltage source, and here one current source. Both are independent current sources. Current sources and voltage sources here. V1 is independent voltage, IS is independent current source. In this case, R4 is connected to the ground, and this ground terminals of V1 and as well as IS are also connected to this. There is a possibility to connect this particular circuit in three different grounds also. Three different grounds. The remaining circuit diagram connections are same for this particular circuit as well as this circuit. This is just an example of understanding how you are going to make the connections while doing the experiments in your laboratories. Coming to the next circuit, slide here, Kirchhoff voltage law. So just with this example of circuit diagram, we'll try to understand what is meant by the KVL. Already you know what is a KVL and what is a KCL. So Kirchhoff voltage law. What's a KVL? The sum of voltages around any closed loop is equals to 0. sum of voltages in a closed loop. Suppose if you consider this is an actually the closed loop. So A, G, H, D are different components connected in that particular closed loop. So sum of voltages of A, G, H, D is equals to 0. That is, two voltage sources or three voltage sources, a positive or negative, whatever it is, but sum leads to 0 in a closed loop. It's not only belongs to this particular closed loop. Suppose if you see this particular closed loop also leads to drop across all the components in a closed loop is equals to 0. Similarly, drop across this closed loop is also equals to 0. So that is actually for understanding sake. Here I am showing the drop across all the components present in a closed loop is equals to 0, or sum of voltages around any closed loop is equals to 0. That is Kirchhoff voltage law. Coming to this example as a quiz in the sense, suppose let us see here, 2 volts drop across the E, minus 1 volt drop across the B, and F here, and drop across H is VH, and in this case minus 5 volts drop across C and 4 volts across G. Suppose in what way we can apply the KVL and evaluate these particular voltages in the sense, let us see first A and B. So if these two components are in a closed loop means sum of voltages are is equals to 0, in the sense VA plus VB is equals to 0, or otherwise here in general based on the polarities of connections of these components we are going to write the equation. So current directions here we are showing like this, that is for component A, current flowing from plus to minus, that is from higher potential to lower potential, while coming to this B, current flowing from lower potential to the higher potential. So now where the current actually enters into the component, what's the polarity of that particular component at the entrance of the current? By considering that particular polarities, we are writing a Kirchhoff voltage law. That's a mesh equation. We'll call it as actually. By applying KVL, we are writing a mesh equation. That is, drop across A component is VA, drop across B component is VB. The current enters from here. Current always flows from higher potential to lower potential. But if the notation is polarities of this component is changing means the drop across that particular component is negative. So positive to negative means drop will consider as positive. That is VA. So negative current enters into the negative terminal means drop across that one is minus VB. So VA minus VB is equals to 0. That is what that indicates, VA is equals to VB. So drop across A component is equals to B component but with the negative polarities. That's why sum of voltages in a closed loop equals to 0. So coming to this KVL, here we have applied independent voltage source of 10 volts and here independent voltage source of 2 volts, and current flowing through this particular branch I1, and here current I3, and here current I2. That means I1 here up to this point I1 is coming here and it's dividing into I2 as well as I3. So current division is taking place here. Afterwards, the drop across this 10 ohms given V naught and 5 ohms, this is 2 volts. Suppose if you observe the total voltage in a closed loop is equals to 0, in the sense this is 2 volts here voltage source is there, and drop across this plus drop across this is equals to 2 volts. So totally that's equals to sum of voltages in a closed loop is equals to 0. So in this way we can calculate voltages, unknown voltages in a particular loop by knowing its some other voltages across the components as well as with reference to the voltage sources. So let us see in this example, suppose if you go for this Kirchhoff current law application here, we are observing according to the Kirchhoff currents law, uh, that is sum of currents entering at a node is equals to sum of currents leaving at a node. That is, In what way we are observing in this, sum of currents meeting at a point is equals to 0. That is, sum of currents entering to the node is equals to sum of currents leaving to the node, leaving from the node. So here just you can observe this particular node point. This is entering current, this one is also entering current, this is leaving current, this one is leaving current. That is, sum of these entering currents is equals to sum of these leaving currents. That's the meaning of sum of I entering is equals to sum of I leaving. In this way we are applying Kirchhoff current law in order to know the currents of unknown branches. So KCL and series circuits. So A, B's are connected in series, these components. So current flowing through this component should be the same. So IA, that is current flowing through the element A, is equals to current flowing through the element B. So that is IA is equals to IB. That means in series, the current amount of current flowing through a series component should be the same. The amount of voltage across parallel connection of components should be the same. So that point you should remember how the current same in case of series, how the voltage is same in case of parallel connection of components. Coming to this KCL application of this example case, Kirchhoff current law, just I have shown you this diagram already. I1 is an input current reaching to this particular node. I2 and I3 are leaving currents from this particular node. That is, I1 is equals to I2 plus I3. This is the nodal equation at this particular node point. I1 is equals to I2 plus I3. So this is a KCL application, KCL example. I'm writing an equation of sum of incoming currents is equals to sum of outgoing currents. Okay, so these are another examples of steady state sinusoidal inputs and how we are calculating the drops across the resistors while applying sinusoidal input voltages. That is, instead of calling resistance in case of uh, in case of sinusoidal input voltages, if you have applied, instead of calling a resistor R, we'll call it as an actually impedance Z. Okay, impedance Z means impedance is the combination of resistance and inductances. Like resistance and inductances means either resistance and reactances. That reactance should be either inductance or capacitance. So impedance is the combination of resistance and reactance. Reactance may be either capacitive reactance or inductive reactance. So here we can observe whenever we are applying sinusoidal inputs, then impedances for that particular state of sinusoidal inputs. So this is the sinusoidal waveform. A sinusoidal waveform here we are observing, that is V of t, that is voltage waveform is represented with the blue color, a current waveform we are representing with the red color. Whenever we are observing the drop across the resistor and current flowing through the resistor, in what way the relation lies in between the current and voltage in case of resistor. That is, in steady state sinusoidal inputs, we are instead of calling resistor, it's an impedance. So Z is equals to, here with the only R, we are representing ZR is equals to R. So current flowing through the resistor and voltage drop across the resistor, if you observe, both are in phase. That is, sinusoidal waveform of the blue color is an actually voltage and red color is current flowing through the resistor. Both are in phase. In this, frequency invariant appears for both resistor as well as voltage as well as current in resistor cases, that is in impedance cases for steady state sinusoidal inputs case. Now coming to this uh, capacitor cases, that is reactance of the capacitor we are denoting with ZC is equals to 1 by 1 over of J omega C. This is the reactance of the capacitor. So in this reactance of the capacitor, in what way we are having relation between the voltage and current, if you observe. That is a voltage, again same blue waveform, and current is actually a red waveform. And this current leads at an angle of 45 degrees as compared to voltage. That is here 1 minute, 90 degrees. Okay, leads 90 degrees as a current leads voltage here. Of course, whatever it is, but here in case of capacitor, current leads a voltage. Current leads a voltage. That's the reason here current is in leading as compared to the voltage. So that's in case of capacitor. Reactance of the capacitor is denoted with the Z is equals to 1 over of j omega c. Similarly, in case of inductance, voltage actually here current lags the voltage. Current lags by voltage. That is, voltage leads current. In that way also we can specify. While observing these waveforms, we can observe this current lags the voltage, or voltage leads the current. In that way, we can define the relation between the voltage and current in case of inductance, which is denoted with the letter L. Inductance, impedance of this inductor is ZL is equals to j omega L. This is 1 by j omega c. In case of capacitor, capacitance impedance, capacitance impedance is ZC is equals to 1 over of j omega c. These are impedances for steady state sinusoidal inputs. While going for the next. Okay, so impedances in series, impedances in parallel. Just Z1, Z2, Z3s are the combinations of resistances as well as reactances. So V is an actually input voltage. So equivalent impedance Z equivalent is equals to, because these three are connected in series. So sum of these three elements leads to the equivalent impedance of the circuit, because Z1, Z2, Z3 are connected in series. Coming to this, Z1, Z2, Z3 or impedances are connected in parallel means, in what way we can calculate equivalent resistance for the parallel combination of three. Similarly, Z equivalent is equals to 1 by, that is 1 by Z1 plus 1 by Z2 plus 1 by Z3. This is an equivalent impedance in case of parallel. These are important formulas to be remembered for series case and parallel case. Coming to the Kirchhoff's laws, like KCL here and KVL here. This is the node point. Input currents are I1 is input current, I2 and I3 are outgoing currents. So I1 is equals to I2 plus I3. Then this is a closed circuit. So according to the Kirchhoff voltage law, sum of voltages in a closed loop is equals to 0, and otherwise Vs supply voltage is equals to the sum of the voltages received by other components, like Vs is equals to V1 plus V2 plus V3. And this way we can define Kirchhoff's current law as well as Kirchhoff voltage law. Series circuits, series RC and series RLC. Suppose if you consider only the passive components R and C in the circuit, this is R and C combinations. RLC means RLC, we are connected in series. Like in this case, the impedance is R and C. In this case, impedance is RLC. Okay, if the capacitor is fully charged, it acts as a volt. Of course, here output we are taking across the C, and this one also output taking across the C. Based on output observing across that component, we are going to calculate the voltages either at the capacitor or at the inductor or at the resistor. Okay, so basic objectives from this particular step onwards, we have steps in this case, transfer functions of particular circuits, and to characterize that particular circuit, and to find the frequency response curves of these circuits. Two-port networks in general will consider the transfer function of the two-port networks we are denoting with h of omega, and input voltage to this two-port network denoted with a sinusoidal signal like V1 or Vi of t, that is the input voltage, is equals to A in cos omega t plus theta. This is magnitude of that particular input voltage, and angular frequency is omega, and theta is the phase angle. Similarly, output voltage V naught of t is equals to A out cos omega t plus theta out. So these are the notations of a two-port network, and with the transfer function of h of omega, with the input voltage of Vi of t, output voltage of V naught of t. So in this case, how we are relating this transfer function with its input and output means h of w, sorry, h of omega Vi is equals to V naught. That is h of omega. Here, what is Vi in terms of rectangular and polar coordinates? If you want to represent this, this is A in at an angle of theta in, and V naught is equals to A out at an angle of theta out. That is magnitude and phase, magnitude and phase. If you are representing this notation in another form, like A out is equals to mod of a transfer function of h of omega into A in. That is the magnitudes if you consider A out in terms of transfer function as well as input magnitude. Then similarly, output phase angle theta out is equals to at an angle of h of omega plus theta in. This is transfer function at an angle of transfer function plus theta in is equals to theta out. So this is an actually a transfer function notation in case of two-port networks. Okay. Uh, So summary of a simple circuits in this R and C are connected in series with respect to the input voltage of Vi, and how we are calculating the transfer function of h of omega, and C and R connected in series but taking drop across the first circuit across the capacitor, here taking drop across the resistor. Based on the taking drop across the components, how its transfer function of the circuit it's varying, just we can observe here. This particular derivative part I'll complete in the next video. Just you can observe in what way we are having the combinations of these RLC components, and in what way we can evaluate transfer function of these RLC circuits. Uh, we'll continue in the next class this particular transfer function evaluation. Okay, thank you.